Welcome everyone to the 2023 Vision Spectra Conference. Thank you all so much for joining us, and in this session you will hear from Trond Boek, the CEO of NEO, the parent company of HySpecs. Trond helped design HySpecs' first hyperspectral imaging system and has over 20 years of experience in the field. Today he is joining us to help viewers working with imaging spectroscopy. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. If you have any technical issues throughout this event, please log out and back in to rejoin the session. Trond, we appreciate you for taking the time to present the 2023 Vision Spectra Conference.
Thank you very much, Jakob, for that introduction. Yeah, so as Jakob said, I'm working as a CEO for NEO. We are the manufacturer of the high-end hyperspectral systems called HySpecs. Today I will be talking about the importance of high spectral fidelity in imaging spectroscopy, and I will do that from an application perspective. I will start to talk about the most important parameters that to keep the spectral fidelity in each pixel very high, and then also what kind of impact those parameters have on the data quality. And in the end, I will take this a bit further and see how those parameters actually influence the classification and quantification results on your hyperspectral data cube. I will quickly start with what hyperspectral imaging is. Hyperspectral imaging combines both imaging and spectroscopy. And there are many different architecture that kind of makes a hyperspectral systems, but we all have the same goal in mind. It's to make a 2D image where each pixel contains several tens to several hundreds of spectral channels. If you only have like quality in mind, your highest priority is the spectral fidelity in each pixel. At HySpecs, we make push-broom cameras, or we use the push-broom architecture, and we do that because we think, or we mean that this has the potential to give you the highest spectral fidelity in each pixel. Yeah, we make cameras from 400 nanometers to 2,500 nanometers on different kind of models, from classical R&D tools to drone systems to airborne solutions to industrial solutions. Okay, let's start. What characterizes a good hyperspectral data? So traditionally, it has been as good signal-to-noise ratio as possible for all wavelengths. The definition of SNR today is not enough. It only takes into account the amount of light that goes through your system and your detector specification. The SNR does not actually evaluate if a photon that is hitting your detector element is supposed to be there or is coming from the correct place in the scene. And there are a lot of other contributing factors that actually impact in data quality a lot more than detector noise sources. That's why this is this SNR specification that you have in your data sheets and so on, they are far from enough to evaluate the data quality, and the spectral fidelity in each pixel. So optical distortions are usually the largest contributor to the lack of spectral fidelity in each pixel. So to evaluate real signal-to-noise ratio in a scene, we need to dig into the optics and the optomechanical architecture. And the largest optical contributions to that compromises the lack of spectral fidelity are in order of importance: spatial misregistration, spectral misregistration, and also for some architecture stray light. In this talk, I will focus mostly on spatial misregistration because this is the largest contributing factor to the lack of spectral fidelity. As I said earlier, we are making push-broom hyperspectral cameras, and in a push-broom camera, we are imaging a very narrow scene about all the channels at one time. So we're using the second dimension on the FBA as the spectral direction. So if you have a point source, in the ideal case, all the energy here should hit on centered on a perfect column on your detector. Of course, optics are never perfect, so the energy from a point source will be spread out, and this is what we're calling a point spread function. And the first kind of and most important spatial misregistration is actually keystone, and that is different spatial sampling for different bands, meaning that the energy, as you see here, will start to leak over to the pixel next to your pixel of interest. In addition, you can have point source variations or point spread function variations. So that means that the shape of the energy is different for different wavelengths. Of course, and then in addition, you can have a combination of these. And in this talk, I will also actually say a little bit about just general blur or just general PSF with larger width. In 2020, we had an article out which is evaluating the different spatial misregistrations from keystone to PSF width to PSF shape. This is one of the plots from that article. This concludes that all of these factors are contributing to the lack of spectral fidelity, but keystone is the largest factor. That's why I will have a main focus on keystone in this talk. We had yet another article in 2014 where we were looking at errors made by keystone. I have cleaned up this graph quite a lot. Then it looks like this. It's made with 100 gigabytes of airborne real data where we have added keystone. And then we looked at what kind of relative errors are we actually getting in the spectra with this added keystone. At HySpecs, we make cameras that are all below 10% of a pixel. So we are down here. And of course, there are many manufacturer cameras today that are up here and also outside of this graph. So this is maybe the most important graph that I will be showing today, because yeah, it's showing you the largest factor to the lack of spectral fidelity in your data. Let's give an example. You can have a camera that has 1000 in signal to noise ratio for a specific band, while that same camera could have like 40–45% keystone. So we will have a 10% relative error in that spectral signature. So of course your real SNR will not be 1000, right? It will be very, very far from that. So that's why it's extremely important that you're not only looking at the top level specification, right? That you're actually digging into what is the spatial misregistration of your camera as well. Sharpness at NEO, we have defined something that we call effective number of pixels. It might be that the terminology will change a bit later on, but currently it's called effective number of pixels. And we define this as the number of native pixels divided by the spatial resolution in pixels. And the same goes for a band. And when you're buying a hyperspectral camera, price per effective pixel is actually a quite good kind of evaluation criteria, right, for buying a camera, because price and our number of effective pixels and the spectral fidelity in each of those pixels, it's what's driving the prices of hyperspectral systems. As I mentioned, the definition of the effective number of pixels, native spatial pixels divided by resolution. But for hyperspectral imaging, in addition, we are adding one definition, which is if the misregistration for one effective pixel is larger than 10%, you have to increase or decrease the number of effective pixels until the misregistration is only 10% of a pixel. I'm coming back to why this is. And we have an article coming out soon from us on this. Okay, let's go now to the application side or the industrial side, where we're going to look at the full solution out in the industry. At HySpecs, we delivered a full solution with software, hardware, computers, and so on for integrating into sorting machines, quality control machines, recycling industry, and so on. We use softwares typically from Predictera. Breeze is the software that is in the lab, you're making your models, validating your models. And once you have a model that works, you export it, and then you can run it in Breeze runtime, which is the real-time solution where you're solving something on a conveyor belt in real time. As an example for this talk, I will use ceramic glass or glass recycling. A big problem today is that people are throwing away ceramic glass with normal glass. When people are using then recycled glass, actually a piece at 1 square millimeter might not actually be melted in the furnace. That can cause then defects in the glass and damage on the production equipment and so on. So it's very important that that the recycling plant is able to sort out ceramic pieces from normal glass. Yeah, and then for training again, typically you have nice clean samples. They are separated, so it's easy to kind of get your spectra of your 3 different kind of ceramic pieces here, ceramic 1, 2, and 3. And on the right side, you have 4 different types of normal glass, float 1, 2, 3, 4. And as you can see, the spectra are very different. So here it's not hard to make a model that kind of classify this is ceramic glass, this is normal glass. But then the question is, what happens to that model when you take it out in the real world? When you take it out to a messy, dirty recycling plant where the objects are on top of each other, next to each other, they are not well separated. So how does then spatial misregistration and large PSF affect the classification result? This is what we're going to look at now. Yeah, so to do that, I have made an artificial scene. So we're taking the spectra from this training data and made here, so the green part here is basically float 1, brown float 2, white float 3. So that is then the background where you have the ceramic glass on top here with different object sizes. So that means that you always have something next to your object now, another spectrum, which is the normal glass spectra. So this is kind of giving you what you can expect in a real environment where all the objects are not separated. To do the classification here, I will use spectral angle mapper. It's a kind of simple way of doing a classification where you're looking at a multidimensional angle, and the lower this angle is, the more similar the spectra are. And for this test, I've been using 0.1 as the kind of threshold for that pixel being part of this class. And again, yeah, so in the data now, I will add keystone and I will add blur to show the effect on the classification results. On the artificial scene where you haven't added any misregistration, of course, you can see this is the output from the spectral angle mapper, where red is ceramic 1, green ceramic 2, blue ceramic 3, and all that's white is kind of floating glass, and black is unclassified. Here it classifies everything perfectly because there is, of course, no misregistration here, and it's perfectly infinitely sharp system. But then, of course, we have to add the keystone. So let's start with 10, 30, 50, and 75% keystone. This is just a false color RGB that you are seeing here. You can already start to see edge effects here, discoloring on the edges. But then how does it influence the detection result? What you can see here on the left side, where we have added 10% keystone, still all objects are detected correctly, all the way down to 1 × 1 pixel. This is a very also important, right? We talked about earlier the definition of effective pixel count and the 10% misregistration limit, right? You have the 30, 50, and 75% as well. On the 30, you start to see edge effects. On the 50, all the edges are either misclassified or unclassified. On 75%, all the edges are unclassified. So meaning you will not be able to detect these objects. Then let's see what kind of how the width of the PSF or the blur of the system affects the results. This is an article out, a figure from an article that was made by FFI, Hans Erling Torkelsen and Torbjørn Skauli. They compared a high-specs camera to a competitor camera. And on the right side here, you can see the contour plots of the PSF, 3 places in the field of view for different spectral channels for high specs. and the competitor here on the left. So in average, the competitor camera is more than 3 times blurry than a high-specs camera. So let's see what kind of effect that can give you on the classification results. So we are adding a Gaussian blur of 3 pixels and a Gaussian blur of 3 pixels plus 75% keystone, right? On the left side, it's only Gaussian blur. So what you can see from that one is that you get a lot of unclassified edges, but not that many misclassification. While when you have a Gaussian blur plus 75% keystone, you get both unclassified and misclassification because you are generating these unphysical spectra based on the object next to it. But look at the worst case here, right? The worst case is ceramic 3 on the float 3 background here. So from this one, you can see that actually a 4 times 4 pixel object is not classified at all in this camera by having this PSF width of 3 times more blurry than the high-spec system and 75% keystone. And a 5 times 5 object only has 1 pixel detected. If you then go to the effective number of pixel definition that we talked about earlier, what will then be the effective number of pixels for such a solution that we have here? Initially, in the artificial scene, it was 75 infinitely sharp pixel. That meant that with no distortions. So that meant that we have 75 effective pixels. Since the spatial resolution is 1 pixel. We blurred the scene and we added 75% keystone. And that actually gave you only 15 effective pixels. So this spatial misregistration with this blur gave you a factor 5 lower effective pixel count and spatial resolution. So it's a huge factor, right? You are expecting 75 pixels, but you're getting 15. And that's why you're not able to detect the 4 times 4 object or 16 pixel object. So to conclude here, keystone and PSF variation, they have a huge impact on the spectral fidelity in the spectrum in each pixel. If you want to have a reliable, repeatable imaging spectrometer that will give you a good spectral fidelity in a pixel without being influenced by the pixel next to it, you need a sharp system and you need low misregistration. And I've heard so many times about industrial systems. People are kind of under the assumption that an industrial system is a worse quality system, and that's kind of completely wrong here. As you can see, it's especially important, right, that for industrial case where it's messy, where it's objects next to each other, small objects, you need a high quality system to solve that industrial solution or that industrial application. And the last maybe and the most important kind of conclusion is that a system with a large percentage of misregistration between bands or between pixels are by nature unreliable, meaning that you can never trust the spectra in your pixel because you can never control what is in the pixel next to your pixel of interest. That makes it by nature unreliable. Thank you. That was my last slide.
Thank you so much, Trond, for joining us and presenting on the importance of high spectral fidelity. Before we wrap up here, I just want to remind everyone in the audience, if you haven't already, you can type your questions and comments into the conference chat. And do not worry, if you've not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the 3rd annual Vision Spectra Conference. Thank you all so much for joining us.